10 minutes to sleep.
10 seconds.
10 seconds. All right. So, good. So now, I'm sure that all of you went through all the calculations that we have done up to now, right? and redid all the calculations up to the point that we reached 2 weeks ago, more or less. I'm certain of this fact. And therefore, I will not repeat all the cluster expansion, which by now you know very well and you understand in full detail, right? I would rather start from the point where we ended up last time, which was the following. We ended up saying that the rank canonical partition function that Mr. Wang calls Q, for reasons that I never understood, but let's use the Wang lecture today, is equal to the sum from 0 to plus infinity, 1 over n factorial, e to the beta mu over lambda cube to the power n times Sn. Okay, so this is essentially the fugacity. This is the normalization of all the integrals that come in the thing, and this is the partition function for the n particle gas. And what we discovered is that this can be calculated in general using the cluster expansion, and it is given by this this funny thing here. Well, let me remind you, this is a sum over all possible cluster configurations, right? So this NLs means I have N1 means I have N1 clusters of size 1 and 2 clusters of size 2 and 3 clusters of size 3. Then B is the contribution to the partition function for each cluster, so BL, actually I should call it BL. Then I had this combinatorial factor that was counting essentially all the ways I could generate such cluster configuration given the total number of particles that I have, okay? And of course, in each Sn, I have cluster configurations which sum up to n, which means that if I sum the cluster size times the number of clusters I have in one configuration, then I should obtain n, right? Otherwise, it doesn't make much sense. Clear? I'm sure that you remember this, right? You do remember this. Why you don't remember this? Come on, guys. I've been in the Philippines and came back, and you didn't study this? What is going on in this class? You don't remember it? Come on, you remember that we had all those points and we were merging them together, and then etc., etc., etc. All right. By the way, in the Philippines, it's raining like here. So it's more or less the same climate, apart from a difference in 20 degrees in temperature. which is felt, right? Somewhat felt, and the wind is much less strong. Okay, so let's move on. So now we have this beautiful result, and it seems to be, and it appears to be very messy. And now I'm going to show you that you're going to obtain from this something really simple and beautiful. So for this sake, we just have to move on with the calculation of this. So this is equal to what? This is equal to the sum over n. Let's plug in the expression for Sn that we found. Sum over n from 0 to plus infinity, 1 over n factorial. Now, I'm sure that all of you think, well, in any case, is never going to be so sadistic to give us the cluster expansion in the exam, and this is true, right? So you're not going to get it in the exam, of course, right? I'm sure that you were dreaming to get it, right?
I was actually going to ask that.
Yeah, so you're not going to get it in the final exam. But, so then you might be tempted to say, okay, so why should I even read it? Why don't I watch a TV series in this class, during this class, right? But this would be a major mistake, because at some point you will have to use similar techniques, unless you use a computer to do this. But at some point in theoretical physics, you will have to use similar techniques, and this is the simplest possible version, which can be done to, up to the, it's a calculation that can be done up to the end. So reading once more this calculation by yourself and asking questions if you will have questions would be highly advisable, okay? For your own education, not for the final exam. Final exam is one thing, your own education is a different thing, and it's much more important than the final exam, okay? You see what I mean? Great, so I'm sure that next time you will have read the notes and be done the calculations, okay? Great. So let's plug in now the expression, sum over NL, product over L, BL and L, and factorial over product over L and L factorial to the power NL. And now let's do some algebra essentially. So first of all, we see that this NL goes with this one. Second, we see that, so here we are summing over N from 0 to plus infinity over all configurations constrained to having the sum over L and L equal to N. Now, I could equally well sum over all possible configurations without any constraint, right? So when I write let's think about it. When I write the sum over N from 0 to plus infinity, sum over NL such that sum over L and L is equal to N of something, this is equal to the sum over all possible configurations without any constraint, right? Because if I sum over all possible configurations without any constraint, well, these all possible configurations will sooner or later be contained in this sum, since I'm summing over all possible ends, right? So, therefore, I can rewrite this as sum over all possible configurations NL of what? Well, first of all, I will have e to the beta mu over lambda cube to the power n. But n is what? N is the sum over L, L, and L, right? Great. And then I will have the product over L of BL to the L, 1 over NL factorial, L factorial to the NL. Okay, so now let's rewrite this stuff a bit better. Sorry, I have to go to the next page. So this is equal to, so let's look at it. I can, well, first of all, I can split this sum, and this will come out to be a product over L of this stuff to the power L and L, right? So you see that I can combine this product with this product and obtain a single product. So let's do that. I will have sum over NL, product over L of e to the beta mu over lambda cube to the power L and L, B and L, over NL factorial L factorial to the power NL. And now I can rewrite this as sum over NL product over L. So here I have, you see that I have a bunch of stuff with an NL here. So I might want to put everything together to the power NL, which is e to the beta mu L over lambda to the 3L times B L divided by L factorial to the power NL times 1 over NL factorial. Right? Right. And now let me put, so let me now look at this. So here I have a sum over all configurations and then a product over L, right? So I could equally well take a product of the sum over N. So I can write this, let me write it and then we explain it if needed. Product over L of the sum over NL from 0 to plus infinity of what stays in here. Is it clear that these two are equivalent?
Is
So-
a change possible because
Sorry?
it's like an exponential.
Well, yeah, of course it's
because
an
it's
so
an exponential.
of course I wrote it this way because now I will do the sum and it will come out an exponential. But first of all, it should be clear that this sum over all possible configurations of the product over L of this stuff is equivalent of the product over L of these sums, right? And the reason is the same reason why, you know, if you take x, x1 plus x2 plus x3 plus x4, right, etc., times y1 plus y2 plus y3 plus y4, etc., is equal to the sum over I and j of xi, yj, the sum of our products. You see, if I add other than y, I add, I don't know, k, blah blah blah, whatever, it's going to see the sum with all the indices of products of the various variables. So the reason I can exchange this with this is exactly the same reason I can go from this to this one. Clear? So that's it. So let me now put this in a, let's put this in a square, and let's put it here. Okay, so this is how it works. Now, as you already understood, the reason I did this is that now I know that the sum from NL from 0 to plus infinity of this stuff is an exponential, right? So what I will get from this is product over L of exponential of e to the beta mu L over lambda to the 3L BL L factorial, and that's it, right? So this is it. And now I notice, so the product of exponentials is equal to the exponential of the sum. So this comes out to be equal to the exponential of the sum for L from 1 to plus infinity of e to the beta mu L over lambda to the 3L BL over L factorial.
Sorry.
Yes.
Can you remind us what L index is?
L is the size of the cluster.
So
So
it can't be
L
zero,
equal
yeah?
1. No, it cannot be
Okay.
0.
Okay, L is not the size of the cluster.
L is the size of the L is the size of the cluster.
I thought that the L was the number of clusters of a given size.
No, NL is the number of clusters of a given
Okay,
size.
that's right.
NL is the number of clusters of a given size.
Alright.
You see? You would have known this if you would have read the notes before coming here today, right? What?
L equals 1 is a single.
Is a single dot.
Yeah.
L equals 2 is two guys got together. L equals 3 is this, plus that, plus this, and then L equals 4 is all possible connected combinations of 4 points, and so on and so forth. Okay, so this is our grand canonical partition function. You see, it's very simple. So this formula, I think, is really beautiful, and that's why you should read these points again. Because not for the sake of exam, but for the sake of immense beauty of mathematical formulas, right? Because this formula tells you that if you want to compute the grand canonical partition function, the only thing you have to know are these coefficients BL, which pertain to, B1 is for a single dot, it's just a volume. B2 is that combination of 3 guys, etc., 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 right? So, this said, why this formula is so important? Well, because you remember that the logarithm of the grand canonical partition function is equal to minus the logarithm of the grand canonical partition function is equal to P over V times K Boltzmann times T. Correct? And therefore, if we take the logarithm of what we found before, we get that this is equal to sum over L from 1 to plus infinity into the beta mu L over lambda to the 3L times PL over L factorial. Full stop. So we just have what we have discovered by doing this cluster expansion in this clever way, is that our equation, so essentially we wrote down a complete perturbative expansion of the equation of state, right? In terms of the interaction, so in terms of clusters, cluster sizes, essentially. And as we will see in a second, so essentially, as you increase the cluster size, you increase the order of your perturbation theory in the density. Okay? So that's what you're doing. All right. So now, when you have this formula, what is the first thing you might want to check? What is the first thing you want to check?
Ideal case.
What?
Ideal guess.
Ideal guess. Correct. So, but now you see that there is a problem if you want to check the ideal guess. You see that here everything is written in terms of the chemical potential as usual for the grand canonical ensemble, while the equation of state, typically you write it in terms of the number of particles. So what we had to do is to express the fugacity in terms of the number of particles at the same order in perturbation theory, and then close the two equations. So that's how we get the equation of state.
Sorry. Are there any cases where B of L is actually some integral to the power of L?
Some integral,
Like B, the B coefficient, B1, B2, and so on are defined using an integral, right? So are there any cases, for example, like B2 is
you
equal
want to write it as an exponential.
Are
Yeah, I see. I don't know. No, I don't. Not that I know.
That would be nice.
That would be cool, yes. So maybe you should do some homework. Maybe I should give you homework. That's a good idea.
For final exam.
No, I should tell Sylvia to give you homework. and then we will grade it.
Oh, no, well, thank you.
Don't be lazy. Don't be lazy. Okay, so now we have to find the number of particles. First of all, let me rewrite this stuff as P over KBT. So I divide both sides by the volume, equal to the sum over L from 1 to plus infinity, e to the beta mu L over lambda cube to the L, and then I'll call B bar L over L factorial, where B bar L is equal to the limit for V going to infinity of BL over V, right? So in particular, B1, you remember, was just a volume, right? So therefore, B bar 1 is going to be 1. So this is the first thing. Now, the number of particles. Well, N over V.
Sorry, what's the importance of the limit?
What is?
Of the limit.
Well, it's not that important, but yeah, well, we can keep it without the limit. I mean, it's just to say that at some point I will take the thermodynamic limit. So you're right. You're absolutely right. It's not important to put it there. All right, so number of particles. This is equal to 1 over V, so density, derivative of the log of Q with respect to mu beta. And if you take this derivative, you see in a second that this is equal to sum over L from 1 to plus infinity of 1 over L minus 1 factorial, and then you will have e to the beta mu over lambda cube to the power L B bar L. So this is our density, right? So in principle now what we have to do, we have these two equations. So what we have to do is we decided which order in perturbation theory in the cluster expansion we want to go. Then at the same order in the cluster expansion, we expand the density and the equation of state. Then at that order in the cluster expansion, we find the chemical potential in terms of the density. We substitute in here, and we have our equation of state written up in the usual form, right? So, for example, let us do it at first order, right? So, trivialities. So, trivialities means we take L equal 1, right? And we keep only the first order term. So we will have N over V equal to L equal 1. 0 factorial is 1. Then we will have e to the beta mu over lambda cube. And then B1, which is 1 again. So this is equal to that. And now we have the P over KBT is equal to L equal 1. So e to the beta mu over lambda cube, then B1 and L factorial, which is 1 again. So therefore this is equal to N over V. And this is the equation of state for the ideal gas. So everything is fine if we do the first order, if we take L equal 1. Take L equal 1, not surprisingly, we're not studying any effect of the interaction, and we just have the equation of state for the ideal gas. So let us now see what happens for L equal to. Well, in that case, the density, N equal to N over V, if I try to write it in terms of Z equal to e to the beta mu over lambda cube. So this comes out to be Z plus z squared times b bar 2 plus higher orders. And this implies that z is approximately equal to n minus b bar 2 n squared plus higher orders. Okay? Now, so now what do we do with this? Well, we go to the equation of state, so P over KBT. If I expand it, it's going to be Z plus Z squared B bar 2 over 2 plus higher orders. And now I substitute the Z, right? And I obtain n minus b bar 2 n squared plus n squared over 2 b bar 2, which means that this is equal to n minus n squared b bar 2. There should be a factor of 2
Over 2.
divided by 2. Okay? And this gives us, you see the structure. This is n over v, so I can rewrite this as n times 1 minus n over 2 b bar 2. This is exactly the same structure as the expansion, the cumulant expansion that we wrote down last time. The difference is that this can be easily improved. Unlike the previous case in which, if you remember, in order to improve the cumulant expansion, we had to account for terms that were subleading in the scaling with the density, with the volume, right, and which we disregarded completely. In this case, we kept everything. So it's just a matter, if you want to improve this, just pick up B3, and that's it. You want to improve it further, put B4, and so on and so forth. You don't know how to compute B4, ask a computer to do it for you. You know, it's very systematic. It's extremely systematic. And in particular, so what we discover if we write stuff properly is that P over KBT in this case is equal to n over v times 1 plus what we called before b2 of t, n over v, where b2 of t is equal to minus 1/2 b bar 2, right? So b2 of t is going to be equal to minus 1/2 integral dq e to the minus beta vq minus 1. Okay? And that's it. So now let us do the calculation of this virial coefficient for particular type of potential. So the van der Waals potential. How does the van der Waals potential look like? Well, we already wrote it once. So it's a spherically symmetric potential, V of Q, which is such that it's equal to plus infinity if the absolute value of Q is smaller than a certain radius or not. So you have a short range, hardcore repulsion, right? So you cannot penetrate within a certain radius. And then you have some long-range attraction. To the power 6 for R greater for, actually, value of Q greater than R naught. Okay? So this is my van der Waals potential. Let us now try to compute that coefficient d2 for the van der Waals potential. So, well, b bar 2.
R naught over R. What's the R there?
What?
R naught over R to the power 6.
Ah, yeah, this is q, sorry, absolute value of q. Apologize. Is it clear now? Okay, so now what is b bar 2? Well, this is going to be equal to, so b bar 2 is just this, sorry, I was doing it on the, you cannot see it. So it's just this without the minus 1/2. This is b bar 2, right? So if we are in the hardcore, the potential is infinity and therefore this is gone and you have just minus 1. So therefore b bar 2 is going to be equal for the hardcore, in the hardcore region as integral between 0 and r naught, dr, and then 4 pi r squared, right? Because I'm in spherical coordinates, of course, in 3 dimensions. And then times minus 1 plus the integral between r naught and plus infinity dr 4 pi r squared, and then I will have e to the beta u naught r naught over r to the power 6 minus 1. Okay? Now, yeah, so let me now assume that u, this interaction strength, is not too large, it's actually pretty small, right? So if I do so, then I can expand this exponential in power series. And then it's clear that this is going to be equal to, well, so first of all, I will have minus 4/3 pi r naught cube, and then plus the integral between r naught and plus infinity dr 4 pi r squared times beta u naught r naught over r to the power 6. This is the leading order. And then there is a quadratic order and so on and so forth. So now if I do this integral, I will get, all of you are able to do an integral of this type, so I don't think I have to do it here, minus 4/3 pi r naught cube plus 4 pi beta u naught r naught cube. So that's what you get. I think there is a factor of 3 missing also here. Yes, there is a factor of 3 missing. Okay. So now you see that this is equal to, you can collect 4/3 pi r naught cube. So this is the radius of the hardcore sphere that is surrounding your molecule. And then with a minus sign times 1 minus beta times u naught. So now let us call this excluded volume omega. So this is minus omega times 1 minus beta u naught. I apologize for the letter omega. I mean, it looks like a solid angle, but it's a volume in this case. So let's write it properly. This thing here, I call it. Okay? So this is the calculation of what happens in this particular case. Let us now plug it in the final formula that we got before, and we will get now that P over K Boltzmann T is equal to what? Is equal to n plus omega over 2 times one minus u naught over kBt times n squared. And now let us do the following. I will first of all collect the two terms that are inversely proportional to kBt and put them on the same side. So you see I have P plus u naught omega over 2 n squared divided by kBt, which is equal to n plus omega over 2 n squared plus etc. etc. Okay? So now, with a bit of, now you have to, imagine things because I'm telling you the final result of a calculation that would involve a higher order expansion in the densities, but this can be seen, this object here can be seen as n divided by v minus n times omega over 2. You see that if you collect v here, so this is n times 1 minus n omega over 2. And if you now expand this, imagining that the density is small, n is small, right? If you now expand this object, you see that the first term is going to be n plus omega over 2n squared, etc., etc. So the second order expansion of this matches this. You see? In n. And also the higher order, but you have to believe me. Now the reason I'm writing this, so I'm replacing single-handedly everything by n over v minus n omega over 2, is that now if I do this, you see that I can write p plus u naught omega over 2n squared times, I take this and I bring it to the other side, times v minus n omega over 2 equal to kd t times n, right? Because I take this kBt and put it on the other side and it multiplies n, and this I took to the other side. So this looks pretty much like P plus A times n over V squared times V minus NB equal to kBt times n. Right? It's the van der Waals equation of state. And now you see what is the meaning of the various quantities in the various van der Waals equation of state. So this one, B is equal to omega over 2. So it's just the volume of this sphere that surrounds your molecule divided by 2. This is the parameter B. The parameter A instead is u naught times omega divided by 2. So it contains information about this volume, this excluded volume, but it's multiplied by the strength of the long-range attraction due to the van der Waals interaction, right? U naught. You remember that this potential was looking like this. We had a long-range tail and the short-range repulsion. So this term here contains information about the long-range tail. This one contains information only about the short-range repulsion. Okay? So by doing this calculation with a cluster expansion, we just nail down what is the physical meaning of the coefficients A and B in the van der Waals equation of state, and we reproduce it precisely. Okay? So before it was a phenomenological equation. Now it's a calculation. Okay? So that's why you should study this cluster expansion. Even though I will not give perhaps. If you are good, I mean, if you behave, I will not give you anything as a cluster. No, actually, I promise I will not give you anything as a cluster.
Can I have two questions?
Yes.
If we take this U0, the long range
Yes.
attracting
Then
force,
you don't have
to zero.
you don't have any modification to the
To the
pressure, but you just have the excluded volume.
And why is, like the excluded volume, why does it contain the half volume of each molecule?
This it's something that, yeah, well, that's what it is.
It's more intuitive to have n times omega, not omega divided
Yeah,
by
it's more intuitive, but probably there is some counting problem.
I mean, if you have like a sphere in the space,
Yeah.
another molecule only will see like the half.
I mean,
The
if
other-
you have
the other
two
half is
spheres, right? If you have two spheres, well, let me think for a second.
So let's do it this way. We have a volume, like a container with volume of V, and I have a single molecule with a volume of omega.
Yes.
And it can move freely throughout whole this container. Now, if I add a second molecule, the volume within which it can move is reduced by omega.
No, it's actually reduced by. Is it reduced just by omega? If your molecule would be a point, right, it would be reduced by omega. But your molecule is another sphere. Look, I don't know. It comes out this way. Let's not. I mean, the factor of 2 is correct. So let's not give it too much of interpretation.
And then here comes the second question. If the potential is attractive,
Yes,
it means that U0 is positive number.
U0 is
Yes.
positive number. Yes.
Then by this, so it means that effective pressure is actually growing instead of getting smaller. And somehow
That is correct. Did I make a mistake with the minus sign? No. It doesn't seem so. Just a second. I think it's correct, but you're right. Yeah, so these are all very good questions. I think you should redo the calculations and check the signs. I might have done a mistake, you know. You see? There might be a mistake. Your physical intuition is correct. So,
maybe on the last, like previous page, there is something.
no, but wait, why the pressure is decreasing? The pressure on the walls is decreasing.
Because like,
Yeah, because they tend to do this.
it has to decrease.
But your volume is decreasing. the decrease in
The
volume
volume
should be compensated by an increase of pressure to have the equality of KBTN.
That is right. No, but I understand the intuition of your colleague. I mean, it's just that I'm trying to think.
But if we are talking about compensation, then the orders are maybe a little bit off. Because
Okay,
the first thing is
let me
order
think.
square.
Let me think about these things,
Okay.
and then maybe we'll discuss it next time carefully. Okay, so I don't want to say anything stupid now because that might be recorded. Okay, so and with this we essentially finish with classical statistical mechanics. Okay, so we're practically done with classical statistical mechanics, and now we start doing quantum statistical mechanics. Good. I want to see some happy faces. Perhaps. No. Too scared of quantum mechanics. Actually, quantum mechanics is what makes statistical mechanics much, much simpler as to compare to classical statistical mechanics, as you will see in a second. So, but before telling you about statistical mechanics, I have to write up some simple facts about quantum mechanics. So, so suppose that you know everything about quantum mechanics, I'm sure, right? Everything. Including what is a density matrix, right? Trace one operator, blah, 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 etc., etc. So now, suppose that we have an operator O and we want to compute the time evolution of this operator, right, in the Heisenberg representation. Then we just average O of t, which means that we are taking initial state psi e to the I h t O e to the minus I h t psi. And now, if we write psi as in terms of the eigenstates of our Hamiltonian, so psi equal to sum over, I don't know, n, cn, n, where n are the eigenstates, then I can rewrite this as sum over n and m, c star m, cn, e to the I, em, minus en, t, times the matrix element m, o, n. Right? We are all familiar with this. Now, this can be rewritten as the trace of a certain density matrix rho with the operator O. Okay? Where the density matrix rho of t is equal to e to the minus I, so formally is equal to this. Which is also equal to sum of n and m, e to the I, em minus en t, and then I have c star, just a second, c star m, cn, yes, m. Okay? Are you convinced that if I take the trace of rho of t with O, I will get this? You are. I see faces of people familiar with this. Great. So now, so this is essentially, this time-evolved density matrix is representing, so I can write it up the time evolution of an operator in the Heisenberg representation, the Schrödinger representation, or I might just consider the time evolution equation for the density matrix itself, which is equivalent to the Schrödinger equation in the Schrödinger picture, and so on and so forth. And in particular, if you pick this density matrix and you try to write down what is the equation it will satisfy, you will see in a few seconds, just by taking derivatives, that this is equal to h rho. Okay? So it's the same equation that is satisfied by the time evolution of operators, with one small difference, that you have the commutator the other way around for the operators. And the reason is that the density matrix is peculiar. The operators you see evolve with e to the iht, e to the minus iht on the two sides, while the density matrix is a projector and evolves with the exponentials put the other way around. Okay? Clear to everybody? Great. So,
isn't the C and C star reversed? The C star should go to Cn.
This one?
Should be without the star, yes.
Yes, you're right.
Yeah.
No, but what is wrong here is, you're absolutely right, but
The sign
there
is
is
something
something wrong here. So this should be n, this should be n, this should be m, this should be m. So let me do it properly. This should be n, n.
No, the
Yes,
first one.
yes, it's
Yes.
correct.
Yes.
It's correct, because
Yes.
look at this. E to the minus I E N T C N N. So e to the minus I E N T C N N, and then M, M. Now it's correct.
Yeah.
Right? You agree? Okay, great. So this is my equation of motion. Now, in okay, so now what happens? Well, so this is the analog, if you want, of the Liouville equation in classical mechanics for density, for phase space density. Now, suppose that we want to ask the following question. We want to ask, so we kick a system, so we have a system that is evolving in time, and then we ask ourselves, so it reaches a stationary state, an equilibrium state, right? And we ask ourselves, how do we describe this stationary state? So in practice, so if you imagine a system that does something and then stays quiet for a long time, goes to a stationary state. So how do you find out what is the stationary density matrix? One way to do it could be, for example, if this guy is staying quiet for a very long time, I just take a density matrix, I average it over time, right? And in practice, since most of the time the density matrix is stationary, I'm going to pick up the stationary density matrix. Okay? So let us do this averaging of the density matrix. If rho of t is equal to this, what we wrote down in the previous, so let me not repeat it, let me just pick it from the previous slide. So if rho of t is this, no, mistake. Okay, so if rho of t is this, now, taking a time average means doing the following. I want to take the limit for t going to infinity of 1 over t integral between 0 and t in dt of rho of t. This is the time average. And now you see that if I assume that the spectrum is not degenerate, so there are no degeneracies in the spectrum of my Hamiltonian, when this energy is different from this one, and I take a time average of this exponential, I will get 0. The only way not to get 0 is if EM is equal to EN. Okay? But when EM is equal to EN, since I'm assuming that there are no degeneracies, that means that M is equal to N. Okay? So in practice, this means that this is equal to the sum over N of Cn squared N. So I think I told you how to do it, but do the calculation explicitly and you will see that this comes out. Non-degenerate spectrum. So this is the stationary density matrix. And now we are ready to play the game of statistical mechanics. So this would be, this stationary density matrix would be an equilibrium state, right, of a system. I kick it out of equilibrium and let it evolve. Eventually it reaches a stationary value. And now I'm asking myself, okay, how will I describe a situation in which I have a microcanonical ensemble? So I have a thermally isolated system, right? And this thermally isolated system has a given energy, and I want that all states within a given energy shell are equally probable, right? Well, it's clear what to do. But the only thing I have to do is to assume, to say that the microcanonical ensemble so the only thing I have to say is that my Cn squared are equal to 1 over certain normalization factor for E smaller or equal than En plus delta, and then 0 otherwise, where gamma of E is just equal to the total number of states that are within the energy shell. Just counting the states. Now imagine a discrete spectrum. Beep, 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 beep. Then you pick up your energy shell, and then you count the number of states that are within the energy shell, one by one. Okay? So that is going to be your gamma phi. And that will normalize the distribution. You see, it's much, much simpler than conceptually, because we are using discrete probability distributions essentially, as compared to the classical one. Because in the classical one we had to do phase integrals, and then we had something dimensionful, we had to normalize it, and so on and so forth. So in particular, in this case, you can ask me, okay, what is the entropy? Wow, that's a nice, looks like a heavy metal. Okay, so this is KB, trace in quantum mechanics, trace of rho log of rho. So this is the definition of entropy it's called the von Neumann entropy, if you have never seen it. And if you now plug in the formulas that we wrote down before, since rho is a diagonal matrix, so it's trivial to compute this trace, you will get sum over n Cn squared log of Cn, and then you will get that this is equal to K Boltzmann sum over, for the microcanonical ensemble, sum over E smaller or equal than En smaller or equal than E plus delta of 1 over gamma of E and then log of gamma of E. But since now, this is just gamma of E, right? You
So
see
where
that
did the minus go?
minus went in here, in the log.
Ah,
This is
okay,
log of
okay.
1 over gamma, so I put the minus inside, put the log of gamma. Then this comes out to be K Boltzmann log of gamma of E. So what is the microcanonical entropy in quantum statistical mechanics? Is K Boltzmann times the log of the number of states in the microcanonical shell. Full stop. Simple, easy, and painless. Okay? Now, why now? If you now want to do semi-classics, you remember all these Bohr orbits around atoms. You remember that stuff, right? So in semi-classical quantization, how do you count the number of states that you have in a given phase space volume? The number of states that correspond to a given phase space volume. Well, you just use the uncertainty principle. You know that delta x times delta p is greater or equal than h bar. I don't remember, over 2, over h bar, roughly. And then you just count the number of volumes of size h bar that you have in your phase space, and that tells you roughly what is the number of states. So that is why the gamma of E that is in that is defined in this way in classical statistical mechanics becomes equal in the semi-classical limit to the integral h to the 3n and factorial. Okay? So now, when you think about it from the point of view of quantum mechanics, this coefficient here that we had to choose to normalize everything is just a Planck constant. I mean, that's the most natural normalization, because actually quantum statistical mechanics, of course, since classical statistical mechanics is a limit of quantum mechanics, quantum statistical mechanics is more fundamental than classical statistical mechanics, and these formulas should be obtained in the semi-classical limit of quantum statistical mechanics. So that's why this h naturally comes out to be the Planck constant and nothing else. In classical statistical mechanics, you could put there whatever you want. And it's never going to enter your final formulas anyway. All right, so now this is it for the microcanonical ensemble. Now what about the canonical ensemble? The canonical ensemble, well, you just define your partition function, which in this case is going to be equal to the sum over n e to the minus beta en, where en are the eigenvalues. This is even much, much simpler, well, if you're able to diagonalize your Hamiltonian to the definition in classical statistical mechanics. And believe me, I mean, if you do the derivation from of the from the microcanonical ensemble to the canonical ensemble, things will be essentially the same in quantum statistical mechanics as they were in classical. In particular, in quantum statistical mechanics, when you want to take an average of an operator with respect to the canonical ensemble, an expectation value, this is equal to the trace of rho canonical O, where rho canonical is equal to e to the minus beta h divided by z, where h is the Hamiltonian of your system. Great. And now, what about the grand canonical ensemble? Well, the grand canonical ensemble is essentially the same as before. I just defined the grand canonical partition function and write it as sum over n from 0 to plus infinity, zeta n Zn Vt. And now in quantum mechanics, well, I can just write this as sum over n from 0 to plus infinity, Zn sum over little n, this is the quantum number of my eigenstates, let me not specified, e to the beta En. This can be also written, if you consider the fact that Z is equal to e to the beta mu, this you can also write as sum over n from 0 to plus infinity, sum over n of e to the minus beta En minus mu times n, its equivalent. And this can be thought of as the trace of e to the minus beta h minus mu times n. So n is the operator that represents the number of particles, h is the Hamiltonian. Have you done second quantization?
Just a bit.
Just a bit. Okay, so you know what is the number operator. Well, you know it in the harmonic oscillator, right? So, and also in general in second quantization will come out. So, in particular, the grand canonical density matrix is going to be e to the minus beta h minus mu n divided by the grand canonical partition function. So you see, if you compare all the complicated stuff in classical statistical mechanics, in quantum statistical mechanics, life is so easy. You have density matrices. The canonical density matrix contains here the energy, right? And the grand canonical density matrix contains energy minus mu n. And the canonical one is just constrained by this thing. So it's nothing special in this sense. So that's it. We have done quantum statistical mechanics as far as I'm concerned. Okay, I'm not going to do anything else. So now we're going to do applications of quantum statistical mechanics. So starting tomorrow, no, not tomorrow, the day after tomorrow, first of all, I'm going to show you how to get the third law of thermodynamics, this story that the entropy is equal to 0 at 0 temperature. And then we are going to discuss ideal quantum gases. So you know that there is a difference between the classical ideal gas and the quantum mechanical ideal gas in the fact that if you have a quantum mechanical ideal gas of identical particles, then you have to take care of the statistics, right? Whether you have fermions or bosons. you will see that statistical mechanics of fermions and bosons is completely different, okay, and leads to observable consequences. So we're going to discuss that, and then we will see. Okay? Good. So I'll see you on Friday.
Still recording.